All right, hello, this is worksheet 14.6, linearization in tangent planes. Let's go ahead and get started. I did not align these very well. Okay, number one, find the linearization of that function at 1, 2. Just as a reminder, the linearization of a function is equal to partial f partial x at x0, y0 times x minus x0 plus partial f partial y at x0, y0 times y minus y0 plus, and then if we have more dimensions, we'll add more terms that look like this. But since we don't, that'll just be plus f of x0, y0. Okay, so let's find partial f partial x. That is negative e to the 2y minus x. Because the derivative of e to the u is e to the u, but then you have to multiply by the derivative of the inside, which here is negative x. And then while I'm at it, partial f partial y is equal to 2e to the 2y minus x. Okay. And so then at 1, 2, I guess I'll say partial. I'm trying to be good notation so that I can be a good role model for you guys. At 1, 2, this is negative e cubed, and then partial f partial y at 1, 2 is equal to 2e cubed. Okay, and so then our linearization, I should also find f of 1, 2. I think that's just e cubed. Okay, so then our linearization is partial f partial x is negative e cubed times x minus x naught is 1 plus partial f partial y is 2e cubed times y minus y0 is 2 plus e cubed. The x0 and y0 in this equation are always the points that you're finding the linearization at. We'll see in the next problem, or not the next problem. The next problem, this will be x0, y0. The problem after that, x0, y0, we have basically two options. It can be either this one or this one. It will end up being this one. It'll be the one that's nicer because that's when we want to do our linearization around. The x0, y0 in general is just a point that we can plug into our function where we'll get sort of nice numbers. Okay, anyway, that's that problem. This is our linearization. Okay, move on to the next one. We want to find the linearization of that function at 1, 1, 0. Okay, just as a reminder, I'll actually just duplicate it. Linearization formula, exactly the same. The only difference is now we're in 3D, so there's going to be an extra term. Now it'll be a function of x, y, and z. And then we also have to add in partial f, partial z, evaluated at x0, y0, z0, and then multiplied by z minus z0. Actually, yeah, these are also evaluated at z0, so I'll just like add arrows down there. The partial derivatives you always evaluate at your starting point. Okay, partial f, partial x. The derivative of arctan is 1 over 1 plus the inside squared. That's x squared plus y squared plus z, or x squared, y squared, z squared. And then I do chain rule, so I'm going to multiply by the derivative of the inside. The derivative of x, y, z with respect to x is just y, z. And so then if I plug in 1, 1, 0, the numerator becomes 0, so that's just 0. Partial f, partial y, it'll be the same thing. When we do the chain rule, it'll be x times z, but z is 0, so again that goes to 0. And then partial f, partial z is the same thing, but this time instead of xz on the top, we'll have xy. But now x and y are both 1. This is 1 over, and then z is 0, so this is also 0. That's equal to 1. Okay. So now I have enough information to compute my, I also should get f of 1, 1, 0, which is arctan of 0, which is 0. Okay. So then my linearization These first two terms are just 0 because both of the partial derivatives are equal to 0 at my point. And so this is equal to 0 plus this last partial derivative is 1. So it's just z minus z0 plus f of x0, y0, z0. But I found just now that that's equal to 0. And then also this here, x0, y0, z0. z0 is also 0. And so I plug in all of those zeros, I add them together, I just get z, which is a very nice linearization. Okay, number 3, use the linearization to approximate f of 2.95, 7.1 for that function, knowing this. Okay, so whenever we're using a linearization to approximate a function, it'll probably give us 2 points. We want to find the linearization at the nicer points. We'll find it at 3, 7. We'll say L of xy about 3, 7. We need to find, and I'm gonna rewrite this, but I'm gonna suppress the points that I'm plugging in. Okay, and then here x0 is 3, y0 is 7, because again, those are the nice points that I want to start at to help me compute the rest. Oh no, I dropped my stylus. Okay, so I need partial f, partial x. That is equal to, partial derivative of the square root is 1/2 times x squared plus y to the negative 1/2, I think. Yep. And then derivative of the inside is 2x. Partial f partial y is again 1/2 times x squared plus y to the negative 1/2. But now the derivative of the inside is just 1. Okay. At 3, 7, this is going to become what? 1/2 root 3 squared is 9, 7 is 7, 9 plus 7 is 16. And then x is 3, so this is going to be times 6. So this is going to be 6/8, which is 3/4. And then partial f partial y is just going to be 1/2 root 16, which is 1/8. Okay. And so then my linearization, also I should find f. Oh, no, it told me f. Okay. So my linearization is partial f partial x is 3/4, x minus 3, plus partial f partial y was 1/8 times y minus 7 plus 4, because f of x0, y0, they gave it to me up here, was 4. Okay, and now it wants me to approximate this value of the function, 2.95, 7.1. So I will say f of 2.95, 7.1 is approximately equal to the linearization of f, evaluated at 2.95, 7.1, which is 3/4 times negative 0.05, right, yep, plus 1/8 times 0.1 plus 4. I don't want to calculate that, but I told someone in my studio they should be able to calculate it, so I should be able to calculate it, right? Or that's hypocritical. So that is, I'm going to get these first two have a common denominator, 3/8 times negative 0.1 plus 0.1/8 plus 4, which is negative 0.3/8 plus 0.1/8 plus 4, which is negative 0.2/8 plus 4, which is 31.8/8, and that's fine. We don't need to simplify it from there. Can you do 0.2/8? Yeah, you can. I just don't want to. Okay. I think 200 is divisible by 8. I'm not sure. No, it's not, actually. That's really sad. Okay. Whatever. So that's our final answer. Again, we're just finding the linearization at our convenient point and then plugging in the new point and approximating it using the linearization. Okay, number 4. Right, okay. So this is where I have to hope that I don't have anything bad open in my Google Chrome window. I just do this? No, okay. I don't actually have anything bad, it's just this. Ooh, I have an email. You guys can't see that. Okay, that is actually an important email. I'll respond to that soon. Okay, let's go to Desmos. And we need to graph the function. Oh, it needs to be Desmos 3D. Frick. Desmos 3D. We need to graph z equals x to the 1/3, y to the 1/3. Okay, and it asks whether we think this can be approximated well by a tangent plane at the center. I'm going to say no, because if you look at this part over here, it's sort of like going upward towards the origin. This over here is going downward towards the origin. Along the x-axis, it's going in at a straight line, same along the y-axis. But if you come in from under, it's going up. This just looks like it's going in all sorts of different directions at the origin, and I don't see how you would use a tangent plane to approximate this. I can zoom in even more. Like, this is just, like, you could try to make the tangent plane straight up, but that wouldn't work for points on the x and the y-axis. You could try to make it flat, but that wouldn't work for points near the z-axis. No matter what you do, you're not going to get a tangent plane that approximates this function well in a neighborhood of the origin. And so I'll just say no. So tangent plane the function cannot be well approximated by a tangent plane. Cannot be well approximated by a tangent plane. And that means it's not differentiable. The definition of a differentiable function in R3 is that it can be well approximated by a tangent plane. That is one way to say the definition. And since this can't be well approximated by a tangent plane, by definition, it's not differentiable. I don't like this alignment, it's annoying me. Okay, so that's that one. Number 5, we want to find the equation for the plane tangent to this graph when x equals 1 and y equals 2. Okay, so again, I'm going to recall from class the normal vector is equal to partial f partial x, partial f partial y, -1. Okay, so, and then evaluate it at x0, y0. Okay, partial f partial x is 1/2 times y minus x to the -1/2 times -1 because of chain rule. This one is the same thing, but chain rule just multiplies by 1, so nothing happens, and then -1. Okay. So let's see, square root of y minus x is equal to, y is 2, x is 1, so there's just 1, which means y minus x to the -1/2 is also 1. So this is just -1/2, 1/2, -1. That's my normal vector. Okay. Now, equation for a plane, 0 is equal to the x component of the normal vector, -1/2 x minus x0, plus the y component of the normal vector, times y minus y0, minus the z component, times z minus z0. Okay. x0 is the value of x that I'm approximating near, or that my tangent plane is tangent to. So that's -1/2 times x minus 1. Similarly, I think y0 was 2. Yep. And then since the graph is described by f of x of y is equal to this, the height is just going to be f of x0, y0. That's going to be our z0. That's the convention for these questions, is that z0 is equal to this. Okay, but I already computed that earlier. Over here, that's just 1. It'll be minus z minus 1. And that is my tangent plane. All right, so hopefully that one is relatively straightforward. As always, feel free to email me if you have any questions, and I think that is it.